Hello and welcome. Today, we're diving into something that sounds like it's straight out of a math textbook, but trust me, it's way cooler. We're talking about Bayes' theorem. But forget about it as just a formula. Think of it as a tool, a secret weapon for thinking, for updating what we believe when we get new information. And we're going to use it to solve a pretty serious medical mystery. So you ready? Let's get into it. Okay, let's kick things off with a scenario. Imagine there's a medical test that's 98% accurate. Sounds pretty reliable, right? You take this test, and it comes back positive. So what's your gut reaction? Panic, right? I mean, 98% accuracy feels almost certain. But here's the twist. Our intuition can sometimes be seriously wrong. So our story starts with a piece of news, a test result that seems to change a patient's life in an instant. But is it really the open and shut case it looks like? Let's find out. I want you to really put yourself in this situation for a second. You feel totally fine, but a routine test comes back positive for a rare cancer. Suddenly, your whole world shrinks down to that one single word on a piece of paper, positive. The stakes are incredibly high, and that 98% accuracy number is just ringing in your ears. Okay, now this slide. This has all the clues we need to crack this case. First, notice how rare this cancer is. Only 0.8% of people have it. That means a whopping 99.2% of people are cancer-free. That's our starting point. Next, the test's accuracy. It catches the cancer 98% of the time in sick people. But, and this is so important, look at that last number. It has a 3% false positive rate. What that really means is if you take 100 perfectly healthy people, 3 of them will get a positive result. 3 of them will be told they have cancer when they absolutely do not. Keep that clue in mind. So before we start plugging in numbers, we need to get our heads around the basic idea here. How do we balance what we already suspect with a powerful new piece of evidence, like this test result? That right there is the heart of Bayesian thinking. It really just boils down to these two ideas. We always start with a prior belief. In our case, the prior is that it's highly unlikely any random person has this cancer, right? Because it's super rare, that 0.8% chance. Then, boom, new evidence drops in, the positive test. Our goal is to use that evidence to create a new, smarter, updated posterior belief. The whole game is figuring out just how much that new evidence should change our mind.
And the bridge between our prior and our posterior, it's something called the likelihood. You can just think of it as the strength of the evidence. How powerful is our clue? In our mystery, the likelihood is all about the test's accuracy. How likely is a positive result if you do have cancer? 98%. And how likely is it if you don't? 3%. The likelihood basically tells us how much weight to give this new clue.
Okay, so we've got our concepts down: prior, likelihood, and posterior. Now, let's bring out the tool that puts it all together, the recipe that lets us update our beliefs in a logical way. Let's finally look at Bayes' theorem itself. And there she is. I know, it might look a little intimidating with all the letters and lines, but don't sweat it. This is just the formal mathematical way of writing down what we've just been talking about. It's a recipe. You put in your initial belief, you mix in the strength of your evidence, and out comes your new updated belief. Simple as that. Let's map our clues right onto this formula. That P of H/D on the left, that's the posterior, the probability our hypothesis that the patient has cancer is true given the new data. That's the answer we're looking for. To get it, we multiply the likelihood, P of D/H, that's the test accuracy, by the prior, P of H, how rare the disease is. Then we just divide the whole thing by P of D, which is simply the total probability of anyone getting a positive test for any reason. We'll get to that part right now. All right, the detective work is done. We have our clues, we have our formula. It's time to put it all together and figure out what the actual probability is that our patient has cancer. Okay, so here's the absolute key. We can't just look at that 98% accuracy and call it a day. We have to figure out the total chance of getting a positive result. And that total pool of positive testers is made up of 2 distinct groups: people who are actually sick and tested positive, the true positives, and healthy people who got a false alarm, the false positives. First, let's figure out the size of that true positive group. We take the tiny chance of having cancer in the first place, 0.8%, or 0.008, and multiply it by the test's accuracy for those people, 98%. That gives us 0.0078. So that's the slice of the whole population that both has cancer and gets a correct positive test. It's a pretty small number. Now, for the other group, the false alarms, we take the huge probability of not having cancer, that's 99.2%, and multiply it by the test's error rate, that 3% false positive rate, and we get 0.0298. Now, wait a second. Just look at those two numbers. The probability of being a healthy person with a false positive is actually bigger, quite a bit bigger in fact, than being a sick person with a true positive. That's the whole mystery right there. So we know the two ways you can end up with a positive test. We know how many people fall into each group. Now we can finally answer the million-dollar question. If you're holding that positive test result in your hand, what are the real odds that you belong to the true positive group? We've followed all the steps, we've crunched the numbers, and the final answer, well, it's almost certainly not what your intuition told you at the beginning. This is where you really see the power of thinking like a Bayesian.
The actual probability that the patient has cancer, given that positive test, is only 20.7%. Let that sink in. Not 98%, not 80%, not even 50%. It's about a 1 in 5 chance. A test that we called 98% accurate leads to a result where you're almost 4 times more likely to be healthy than sick. Wow.
So how on earth did we get such a shockingly low number? Well, this quote really nails it. The final answer is powerfully, almost completely, shaped by where we started, that prior probability. The single most important clue in this entire puzzle was how rare the disease was to begin with. Let's just break it down one last time. Because the disease is so incredibly rare, the group of healthy people is absolutely massive compared to the tiny group of sick people. So even a small error rate, just 3%, applied to that huge healthy group, creates a way bigger number of false alarms than the high 98% accuracy does when applied to the tiny sick group. At the end of the day, the rarity of the disease just completely outweighs the accuracy of the test. And what's so cool about this is that it's not just some weird medical brain teaser. This exact way of thinking is the fundamental logic behind so much of the artificial intelligence that's all around us. This is how machines learn from data. Just think about your email's spam filter. It starts with a prior belief, a general idea of whether an email might be spam. Then it sees new evidence, maybe a word like lottery or winner. And with each new clue, it uses Bayes' theorem to update its belief, making it more and more certain it's spam. It's this simple loop. Start with a belief, get new data, update your belief, and just repeat over and over and over. That's learning. And that really brings us to the big takeaway here. Bayes' theorem is a powerful reminder that while strong evidence matters, our starting assumptions, our priors, matter just as much, if not more. It's a call for a healthy dose of skepticism. So the next time you hear some shocking statistic or a claim that seems definitive, just take a second and ask yourself, what's the baseline here? What was the prior probability? Because as we've seen today, understanding that can change absolutely everything.